In this video, we're going to cover what NMR is and how it works, carbon-13 NMR, and hydrogen NMR. NMR stands for nuclear magnetic resonance. This kind of spectroscopy is one of the techniques scientists have to identify the structure of a molecule. In NMR, it uses the different kind of environments different atoms have to generate a spectrum which can give us information about where those environments are in the molecule. To do NMR, you put a sample in a small tube like this, place it in a big machine like this, and it will generate the spectrums we're going to look at throughout this topic. We're now going to look at the process through which NMR works. You would not need to explain this in detail in your exam, but this will give you the context of how it works for when we look at the different features of NMR later in this video. The nucleus of some atoms have a spin, so the nucleus overall can either be spinning up or spinning down. The atoms which have a spin are those with the odd number of nucleons, and a nucleon is just a way of saying a proton or a neutron. In this case, it doesn't matter whether it's a proton or a neutron. So if we have an odd mass number, it means we have an odd number of protons and neutrons in the nucleus, and therefore, overall, there will be a spin of that nucleus. So each of hydrogen, 13 carbon, 19 fluorine, or 31 phosphorus, for example, will have a spin. You could do NMR on any of these different atoms. In A-Level Chemistry, we're going to be focusing on hydrogen and carbon NMR. When a nucleus has a spin, it generates a magnetic field around itself. The effect of an external magnetic field on each nucleus is different, depending on its environment within the molecule, which we'll look at later in the video. So for the moment, let's just imagine we've got an external magnetic field in the up direction. And we placed a hydrogen inside that magnetic field. The hydrogen could either be aligned within the magnetic field, so they're both spinning up, or the hydrogen could be aligned against the magnetic field, spinning down. If you consider the sheer number of hydrogen atoms you would have in a sample of a molecule, 50% of them would be spinning up and 50% of them would be spinning down. So the size of the energy gap between a nucleus being aligned or against the magnetic field is determined by the strength of the magnetic field around that nucleus. Each nucleus will be in a different environment, which we'll look at in a moment, and that means it'll absorb energy at different frequencies. Therefore, we can measure what frequencies have been absorbed or not absorbed and use that to generate a spectra. Before we look at the different environments within a molecule and the spectra they generate, we need to look at what solvents we can use to dissolve that sample in to place it in the NMR machine. In A-Level Chemistry, we're looking at hydrogen NMR or carbon NMR. This means that any hydrogen atoms will appear in the NMR spectra. Therefore, it's important that the solvent we use doesn't contain any hydrogen atoms, as you would only see the result of the solvent hydrogen and not your sample. So for example, water would be a really bad solvent to use because you would just see a peak for the H atoms inside the water molecule and no peaks for your sample which you're actually trying to look at. We often use deuterated solvents instead. Their 1H hydrogen atoms have been replaced by deuterium, or 2H. Deuterium is an isotope of hydrogen that's got two nucleons, a proton and a neutron. So since there is an even number of nucleons inside the nucleus, there'll be no overall spin, and therefore it won't interact with the magnetic field and cause a peak on the NMR spectrum. Sometimes other solvents such as CCl4 can be used. It doesn't contain any hydrogen atoms, or we could use CdCl3, again having a deuterium in the place of a hydrogen. NMR machines need to be calibrated, so we can compare the results of different machines looking at different molecules. We use a chemical called TMS as a reference chemical, so we use TMS as a 0 point on the spectra. TMS is tetramethylsilane, and this is a silicon atom with 4 methyl groups coming off it. The reason we use TMS is that it only gives one hydrogen signal or one carbon signal. We'll look at this later on, but it has all 12 hydrogen atoms in identical environments and all 4 carbon atoms in identical environments. So this means that you'll only produce a single peak in both. This peak is what we set the value of the chemical shift, which we'll look at later, as 0. So this way we can consider the TMS being added to the compound for a calibration purpose. We know what the 0 peak is, and all the rest of the peaks in our sample are always measured relative to TMS. We also use it because it is a non-toxic chemical. It is inert, so it's not going to react with our sample before we have time to get the NMR results. It has a low boiling point, it's a volatile chemical, so it's very easy to remove from the sample after we have done the NMR. And the peaks given by using TMS are far away from all the peaks we'll see in other organic groups, so we're not going to get the TMS peak confused with a peak from the target molecule we're looking at. NMR gives us information about carbons or hydrogens in different environments. We can think of an environment as being a unique part of a molecule. And this is because a nucleus is partly shielded from the effects of the magnetic field based on the surrounding electrons. And depending on which atoms or groups are attached to a nucleus, that will affect the amount of electrons around it and therefore its shielding. So therefore the shielding of each nucleus is different if that nucleus is in a different position of a molecule or in its own environment. We're going to look at several worked examples to illustrate this concept. To start off, we're going to look at bromoethane. This carbon is in a unique environment. This carbon is different from this carbon here. Now that's quite obvious in this example, as we've got a CH3 attached to a CH2 and a Br, and this is a CH2, so obviously not the same as the CH3. So therefore we could say that this carbon is in a different environment from this one. So for bromoethane, we would have 2 carbon environments, this one and this one. We're also looking at hydrogen NMR, so let's now consider the hydrogens in the molecule. Well, all these 3 yellow hydrogens are identical. We've got free rotation of single bonds around an atom, so each of these hydrogens could be interchangeable with each other. And that's a general rule for NMR spectroscopy. Any hydrogens on an atom are considered in the same environment. So for example, each of these hydrogens are in the same environment, and they're obviously different from these 2 hydrogens here. These are 3 hydrogens on a carbon, these are 2 hydrogens on a carbon with a Br and a CH3. So these 2 hydrogens here would be in a separate environment, as they're different from the yellow ones. It's useful to label the environment so we can label the spectra later on and make it clear what environments we're talking about in an exam. This saves the examiner getting confused if we have got similar parts of a molecule. So rather than trying to describe a CH3 environment, for example, we'd label this environment A, and in this video I'll use lowercase for the hydrogen environments. And we could say that the green hydrogens are in environment B. You'll only look at either hydrogen NMR or carbon NMR at once. The spectra can only show one type of environment. We could run both carbon and hydrogen on the same molecule, but we would get two different spectra at the end. So we only need to consider either the carbon environments or the hydrogen environments. We can identify both sets of environments on the same molecule, but you wouldn't expect to see both sets on the same spectra at once. We'll now look at a slightly bigger molecule, this time 1-bromopropane. Just like last time, we can say that this carbon is in a different environment from these two carbons here. This is quite obvious because this is a CH3 and the other two are CH2s. So this carbon is obviously different from the other two. However, both CH2s won't be in the same environment. We have to consider the molecule as a whole. So, for example, even though that this is a CH2 and this is a CH2, the carbons are in different environments because if you think about it, the green carbon has got a CH3 on one side and a CH2 on the other, while the blue carbon has got a CH2 on one side and a bromine on the other side. Therefore, the different parts of the molecule mean that these are in different environments. Even though they're both CH2s, the environment of this one, a CH3, CH2, then a Br, is different to the environment of this one, a Br, and then a CH2 and a CH3. So this molecule would have three separate carbon environments. We'd also have hydrogens in the same environment. So we've got, so far, one carbon environment and one hydrogen environment, labelled A. We would label the second set of environments B, and the final set 3. So 1-bromopropane has got 3 carbon environments and 3 hydrogen environments. We'll now look at ethanol. So again, as before, this might appear straightforward in that we've got a CH3, which is obviously different from a CH2, so that will be our first carbon environment. The CH2 is obviously different to the CH3, so that will be our second carbon environment. And since we're looking at both carbon and hydrogen environments in this case, we've now got a hydrogen on the OH, and this hydrogen is obviously different to the hydrogens on the CH2 and the hydrogens on the CH3. So we could label the first carbon environment A and the first hydrogen environment lowercase a, the second carbon environment uppercase B, the hydrogen environment lowercase b, and now we have an additional hydrogen environment which we could label C. So ethanol would have 2 carbon environments and 3 hydrogen environments. You can have different numbers of carbon and hydrogen environments on different molecules. You won't always have the same number of each. We'll now look at propane. And we can see that we have got a CH3 here, so our carbon and therefore hydrogen will be in our first environment. And the end CH3 will also be the same environment as the first, as both of these environments are identical. It's a CH3 attached to a CH2 attached to a CH3. It's a CH3 attached to a CH2 attached to a CH3. So you can see the way I've described these two parts of the molecule were identical to each other. Therefore, these carbons and hydrogens will be in the same environment as each other. The CH2 in the middle is obviously in a different environment to the yellow CH3s. In this case, it's quite obvious because it is a CH2 and the others are CH3s. So all of the yellow carbons and hydrogens are in the same environment, which we can call A. And the CH2 in a separate environment, which we'll call B. So propane has got 2 carbon environments and 2 hydrogen environments in total. Each carbon won't necessarily have its own environment, so we can have 3 carbons, but only 2 environments. We'll now look at a slightly longer example still. This case, this is pentane. So just like before, both of the CH3s at the end of the molecule will be in the same environment as they are the same. We've got a CH3 next to 3 CH2s and then a CH3. We've got a CH3 next to 3 CH2s and then a CH3. I've described those exactly the same, therefore they must be in the same environment. These CH2s will be in the same environment as each other. It's a CH2 with a CH3 on one side and then a CH2, CH2, CH3 on the other. It's a CH2 with a CH3 on one side, then CH2, CH2, CH3 on the other. Again, you can see how I've described their position the same, taking into account the whole molecule, not just what they're directly next to. If I've described that the same, therefore they are in the same environment. The CH2 in the middle is in a different environment from the CH2s either side of it. The blue CH2 has got a CH2, CH3, CH2, CH3 either side of it, while the green ones have got a CH3 next to them and then a CH2, CH2, CH3. So you've got to consider its position in the molecule as a whole, not just if it's a CH2 or a CH3. So in this case, both of the yellow carbons are in the same environment. Both of the green carbons are in the same environment. And the blue carbon is an environment of its own. So propane will have 3 carbon environments in total and 3 hydrogen environments in total. This molecule might appear slightly more complicated, but we'll go through exactly the same process we've done so with all the other examples. These 4 carbons are all in the same environment. They are all CH3s attached to a carbon with a CH3 with a CH3 twice onto it. If you look at each of these 4 carbons, they are all identical if you try to describe them, therefore they are all in the same environment. The 2 carbons in the middle are in the same environment. Again, they are each carbons with CH3s twice, a hydrogen, next to a carbon with CH3s twice, and a hydrogen, therefore they're in the same environment as each other. So this molecule has got 4 carbons in the same environment, so we'll call that environment A, and 2 carbons in the same environment as each other, which we can call B, so the molecule has got 2 carbon environments and 2 hydrogen environments. This is TMS, which we looked at earlier. We said it was a very good calibration chemical to use because it only gives a single peak for each environment. So let's look at why that's the case. Well, we've got 4 carbons in the same environment and 12 hydrogens in the same environment, as each of these CH3 groups are identical to each other. That's why it gives a very strong signal in the same place for carbons and the same for hydrogens. We're now going to look at how NMR measures the difference between the different environments. The difference between the energy in an environment and that measured in the reference standard TMS is called chemical shift. We use the delta symbol to represent this, and it's measured in parts per million or ppm, and this is the difference between the signal we've measured on the sample and that of the reference standard. So for example, on an NMR spectrum, we would set the TMS signal as being 0, and then you might have different peaks at various points on the spectrum. For carbon NMR, the spectrum ends at around 220, and you'd then be able to identify where the peaks are at various points along the spectrum. Now, the chemical shift depends on how shielded a particular environment is. The more shielded an environment is, the closer to the right it will be on a spectrum. The more de-shielded it is, the further it will be towards the left. So for example, there is little effect on shielding in a carbon-carbon bond, therefore we normally find these towards the right of a spectrum at about between 5 to 40 ppm. A carbon bonded to an oxygen will be slightly de-shielded as the oxygen is electronegative, it's withdrawing electron density away from the carbon, therefore the carbon will have a greater interaction with the magnetic field. This means it will be shifted downfield or to the left. So if your carbon, or a hydrogen if you're looking at hydrogen NMR, is next to an electronegative group, that will affect the shielding on your carbon or hydrogen and cause it to be shifted what we call downfield. If we had a carbon bonded to an oxygen with a double bond, so for example an aldehyde or a ketone, then the electron density in the carbon would be even further removed by that oxygen, so it would be shifted even further down than the carbon-oxygen single bond. On your chemistry datasheet, which will be given in the exam, for each type of carbon or for each type of hydrogen, you're given a chemical shift range where you could expect to see that on the spectrum. As you will notice, the more electronegative an atom is attached to a carbon, the further down the shift it is. So for example, carbons to carbons are at the top, but carbons with aldehydes or ketones or esters or carboxylic acids are further down. The same can be true for hydrogens, so hydrogens next to carbons are further up, hydrogens which are part of carboxylic acids or aldehydes are further downshifted. So you can use this table to try identify roughly which group you've got, but generally the approach you'll use is the more downshifted something is, the more electronegative that group is, and we'll look at some examples of that in a moment. Carbon-13 NMR gives us two useful pieces of information. The number of peaks on a spectra correspond with the number of carbon environments, so each environment will have its own peak. And as we've just looked at, carbons which are less shielded, so closer to electronegative groups, will have a higher chemical shift. So we can find out the number of environments on a molecule and roughly whereabouts those environments are, depending on how electronegative or how downshifted those groups are. We'll now go through some worked examples of how to identify the different peaks for different molecules. To start off with, we'll look at ethanol. The first thing to do for each of these cases is to draw out the molecule. We'll then identify environments, and remember we're just looking at carbon NMR at the moment, so we're only looking at carbon environments. We've got one environment here in yellow and a second environment here. If you're struggling to identify why these are different environments, watch the previous section of the video again. For these examples, I'm going to assume that you're confident in identifying correctly the different environments on a molecule. We're then going to label each of the environments, so we can match the label of the environment up to the spectra. This will make your answer really clear in an exam. The first peak on the spectra would come from environment A. We've got two different environments and two different peaks, so we know that we've assigned our environments correctly. If, for example, we thought we had three environments but only two peaks, then we'd have made a mistake somewhere and would need to go back and check. So we've got a choice of the two environments to match up to the spectra. We've got a CH3, which is next to a CH2, and then an OH, or a CH2, which is next to a C and an OH. From what we've just looked at, we know that this is going to be the most shielded group, or the one next to the least electronegative part, because this group here is next to the OH. So therefore we'd expect the CH3 next to the CH2 to be further to the right, and the CH2 next to the OH, the electronegative group, to be further to the left. Therefore, peak A, the furthest to the right, will be the CH3, and peak B, the furthest to the left, will be environment B, as it's next to the OH group. That matches up roughly if we look at the values on the bottom with our data sheet. So for example, peak A is a CC group. We'd expect that to come between 5 and 40, and this peak is at approximately 20. Peak B on our spectrum is about 60, which is in the range of 5 to 90, where we would find alcohols, ethers, or esters. So we can therefore assume that we've correctly assigned these peaks. We're now going to look at ethane. So we would draw out the molecule, assign the environments, and then label the environments. In this case, it might appear quite straightforward that there's one environment, therefore one peak, so this peak has to be environment A. The reason I've shown this example is that even though there are 2 carbons in environment A, there is still only one peak, as it is one peak per environment, not per thing in that environment. So it doesn't matter how many lots of environment A we've got on a molecule, we're still only going to have one peak for environment A on our spectrum. If, for example, we had a different molecule with only one environment and we were comparing 2 different environments, we can still be confident that this is the ethane spectra, as our peak is at about 10 ppm, well within the range of a CC carbon. So as well as checking the number of environments to the peaks, also consider the ppms for carbon NMR. We'll now look at butanone. So we would draw out the molecule first, assign all the environments. In this case, we have got 4 different environments. And then we would label the environments so we can add the labels to the different peaks here. It's much better than trying to draw a series of arrows, which could get confusing in an exam, or try and describe it as a CH3 peak because, for example, we've got 2 CH3s on this molecule. So always label your different environments, and that'll make it a lot easier for the examiner when they're marking your work. This peak here would be environment D. That is because D has got the least effect of electronegative groups nearby, so it's the furthest away from the oxygen, which we know is electronegative, therefore we'll find it furthest to the right. It also makes sense, as D is around 10 ppm, which is well within the range for a CC carbon, which D is. So D is the first one we can assign. The next 2 peaks are A and C, as these are the next furthest away from the electronegative group of the oxygen. In this case, it'll be very tricky to decide which order A and C go. You could have those in interchanging places. So for example, this peak here could be environment A, and this peak here could be C. Both of these groups are very similar to each other. It's going to be hard to tell apart which would be the one which is further shifted downfield, because they're both to the adjacent carbon with the electronegative group. You wouldn't need to assign their exact positions in the exam, just recognise that these are close together because these 2 groups are very similar here. And that could help you compare 2 different carbon NMR spectra, which we'll look at in a moment. Finally, peak B will be all the way at the end. This is about 210 ppm, which matches exactly where you'd expect to find an aldehyde or a ketone. It's the furthest shifted downfield, to the left, because the carbon is the closest to the electronegative group, in this case, the oxygen. Now we're going to look at cyclohexane 1,3-diol. So we would draw out the structure of the molecule. We would then assign the different environments and label the different environments. This would be environment D, as carbon D is the furthest away from the electronegative groups, in this case the OH, therefore it would be the furthest upfield, the furthest to the right, again fitting well within the range for a carbon-carbon bond. The next 2 peaks could either be C or A. Just like we looked at in the previous example, it can be difficult to assign these environments precisely when you've got two carbons which could be quite close together in terms of how far away they are from electronegative groups. In this case, both environments C and A are on the carbon adjacent to the electronegative group, therefore it'd be hard to precisely decide which one was which. B will be the environment which has got the most de-shielding, therefore the furthest to the left, fitting within the range where an alcohol is within 50 to 90 at about 60. If you compare this example to the one we did a moment ago, both of these molecules had 4 environments. So if you're trying to compare the two molecules to the two spectra, you couldn't just do it based on the number of environments alone. You'd have to look at the chemical shifts. Now, even though in both cases we had two which could be interchangeable, the difference in position of the electronegative one, in this case an alcohol at around 60, and the one we looked at a moment ago, a ketone, which was about 210, we could differentiate between these two examples based on the position of the electronegative group. So they both have 4 peaks because they've each got 4 environments, but the position of the electronegative one was different in each case, which would allow us to tell them apart. In the exam, you might get questions asking you to identify a couple of molecules from a couple of different spectra. So for carbon NMR, you've always got to use a combination of how many environments and how many peaks, and then using the shifts in your knowledge of electronegativity to determine where they come on the spectrum. We're now going to look at hydrogen NMR and the information that gives you on its spectrum. Just like with carbon NMR, each peak on hydrogen NMR equals a different hydrogen environment. Hydrogen NMR also gives you 2 additional pieces of information. We have something called integration traces, which give you the number of hydrogens in each environment, and splitting can tell you the number of hydrogens in adjacent environments. So hydrogen NMR can give you a lot more information compared to carbon NMR. We'll now look at both integration and splitting separately to see how they work, and then we'll go through some worked examples putting all of these together. Integration in a hydrogen NMR spectra tells you the number of hydrogens in total in that environment. So for example, if we imagine this was our hydrogen NMR spectra, integration is sometimes shown in 2 different ways. Sometimes you're just given the number directly above the peak, and if you use this on modern NMR machines, it will automatically calculate the integration for you. And sometimes it is shown with a symbol like this. You can manually work out the integration from the data given on an NMR, and we'll practice that in a moment. So let's just look at chloroethane. And we would have 2 different hydrogen environments on the molecule. In this environment, there are 3 hydrogens in total. And in this environment, there are 2. So our integration traces for the yellow peak would show 3. The integration trace for the green peak would show 2. And this is really useful because we can then work out how many hydrogens are in each environment just by looking at the spectra. We'll now do another worked example looking at propane. And we have 2 different environments on propane. We've got 2 lots of the yellow environment and 1 lot of the green environment. The yellow environment would have an integration trace of 6 because there are 6 hydrogens in total in this environment. In the green, there would be a total of 2. If the NMR spectra doesn't automatically work out the integration for you, based on the length of the integration trace on the spectra, you would measure the lengths of these spectra, quite often in millimeters, and you can then use that to work out the actual integration values. Integrations are always given as a ratio. So for example, if you measured the integration traces of 4 different peaks, you might have values of 0.6, 3.6, 1.2 and 1.8. Now obviously there aren't 0.6, 3.6, 1.2 or 1.8 hydrogens per environment. This is just the simplest ratio of these. In order to work out the number of hydrogens in each environment, we divide each of these values in the ratio by the smallest. In this case, dividing each of these by 0.6, which would then give us values of 1, 6, 2 and 3. So it's likely that in environment A we would have 1 hydrogen, 6 in environment B, 2 in environment C, and 3 in environment D. Now remember that as integration traces are always ratios, you might actually have 2 in A, 12 in B, 4 in C, or 6 in D. So just bear that in mind with the harder exam questions. Sometimes you might have to double or triple the values stated to get the actual number of hydrogens in each environment. Splitting tells you the number of hydrogens in adjacent environments. So let's just look at chloroethane. We have 2 environments in chloroethane. If we look at the yellow environment, there are 2 hydrogens adjacent to this environment. So we're not looking at the number of hydrogens which are yellow, we're looking at how many hydrogens are on carbons next to this one. So the adjacent carbon to this environment is this carbon here. On this carbon there are 2 hydrogens, so we would say that there are 2 hydrogens adjacent to this environment here. Therefore, the green environment would have 3 adjacent hydrogens. So on the carbon adjacent to this one, which is this one here, there are 3 hydrogens in total. We'll now look at 2-chlorobutane. And this molecule would have 4 different hydrogen environments. The yellow environment has got 1 adjacent hydrogen, because on the carbon next to it, there is 1 hydrogen. The green environment has got 5 adjacent hydrogens. On the carbons next to the green environment, there are 3 hydrogens to the left, 2 hydrogens to the right, for a total of 5 adjacent hydrogens. The blue environment has got 4 adjacent hydrogens. It's got 3 to the right and 1 to the left. And the red environment has just got 2 adjacent hydrogens, because on the carbon, next to the carbon in the environment, there are 2 attached. We're now going to look at propane. So we would assign the environments as before. Now, environment A has got 2 adjacent hydrogens. When we're looking at the adjacent hydrogens, we only consider one example of that environment. So I've got 2 options here because I've got 2 sets of hydrogens in environment A. If I'm looking at this example here, I wouldn't repeat the process for anything else in this environment. So, for example, adjacent to the yellow environment is 2 hydrogens. It doesn't matter that there are 2 hydrogens adjacent to that environment twice, we don't double count. So we just look at one example of that environment, and each of the yellow hydrogens, no matter what position we look in the molecule, has got 2 adjacent to it. So in this case, the yellow environment has got 2 adjacent. The green environment has got 6 adjacent hydrogens, because each green hydrogen has got carbons next to it for a total of 6. It doesn't matter that the ones in different environments are each in the same. In this case, yellow is different from green, so it doesn't matter that there are 2 examples of yellow either side of it, because we're looking at this environment here. So you only count each environment once, but if you're looking at one environment, different environments, even if it's the same one, to count. So yellow has got 2 adjacent, green has got 6. Let's look at an example now of ethane. And we'll assign the environments. Now ethane is adjacent to 0. We've got to be careful here because there's only one environment in this molecule. We don't count its own environment when we're looking at adjacent hydrogens. So if I'm looking at the yellow environment here, I can't count any yellow hydrogens when I'm looking at adjacent hydrogens because they're not actually adjacent, they are the same hydrogen. So there are no hydrogens which aren't yellow on an adjacent carbon to this environment, therefore there are 0 adjacent hydrogens. Finally, we'll look at ethanol. So we'll assign all the environments as before. In this case, we've got 3. The yellow environment is adjacent to 2 hydrogens. The green environment is adjacent to 3, and that's because we don't count any OH hydrogens or any NH hydrogens in terms of splitting. There are 3 environments, and there will be 3 peaks on the spectra, but OH and NH hydrogens never split anything else, and they are never split themselves, so we don't count it for splitting. So if we're looking at the green environment, we've got 3 adjacent hydrogens to the left, an OH to the right, which we don't count, therefore there are just 3 adjacent hydrogens for the green environment. The blue environment is adjacent to 0, because remember, OH and NH hydrogens are never split, and they don't split anything else, so we don't count them or look at them for adjacent environments. So we'd consider the OH to be adjacent to 0. We're now going to look at what splitting actually is. Each peak on a hydrogen NMR spectrum is split into mini peaks depending on how many adjacent environments they are. To work this out, we use something called the N+1 rule. And this is the number of adjacent hydrogens plus 1. So for example, if I had 2 adjacent hydrogens, my peak would be split into 3. 2 adjacent plus 1 equals 3. So if my N+1 equals 1, that means I've got 0 adjacent hydrogens, as 0 plus 1 equals 1. So I would just have a singular peak like we looked at in carbon NMR. And we call this kind of peak a singlet. You have to know the names given to the different types of split peaks. If N+1 equals 2, it means there is 1 adjacent hydrogen, as 1 plus 1 equals 2. This means our peak will be split into 2 peaks. And we call this a doublet. If N+1 equals 3, it means there are 2 adjacent hydrogens, as 2 plus 1 equals 3. And our peak will be split into something which looks like this. Note the different heights of the peak. So we've got a smaller peak, a large peak, and a smaller peak. And we call this a triplet. If N+1 equals 4, it means we have 3 adjacent hydrogens, as 3 plus 1 equals 4. And this is what that peak would look like. Again, note the relative heights of each of the different peaks. And we would call this a quartet. If N+1 equals 5 or more, so if you've got 4 or more adjacent hydrogens, the peak will be split into something which roughly looks like this. Now the peaks get kind of messy when you've got 4 or more adjacent hydrogens, so you just notice there's quite a few peaks next to each other. It won't be quite as obviously defined as these peaks here. And we just call anything with 5 or more a multiplet. So we'll now look at some worked examples for these. We'll start off by looking at butanone. And this has got 3 hydrogen environments. Starting with the yellow environment, it's adjacent to 2 carbons. 2 plus 1 equals 3, following the n+1 rule. So the peak for the yellow environment would be split into 3. It would be a triplet. The green environment has got 3 adjacent hydrogens. So 3 plus 1 equals 4. And the green environment would be split into a quartet, so that peak would look like this. Finally, the blue environment has got no adjacent hydrogens. 0 plus 1 equals 1. So the peak for the blue environment would be a singlet. We'll now look at a series of examples as how to identify the peaks for hydrogen NMR spectras. We'll start with chloroethane. The first thing to do is draw out the molecule and to highlight the different environments. In this case, we've got 2 different environments. We'll then label the environment so we can add them to our spectra. In this case, we've got an A environment for the CH3 hydrogens and a B environment for the CH2 hydrogens. Hydrogen NMR contains a lot of information. You'll often get lots of marks in the exam for breaking down the information each environment and each peak gives you. It's not just a case of assigning the peak to the environment, you've got to specify all the information you can gain from that environment. We'll start with environment A. There are 3 hydrogens in environment A. A is adjacent to 2 hydrogens. Therefore, we'd expect A to be a triplet. We'll now look at environment B, which has got 2 hydrogens in its environment. It's adjacent to 3 hydrogens. So we'd expect it to be a quartet, following the n+1 rule in each case. 2 plus 1 equals 3, which is a triplet. 3 plus 1 equals 4, which is the quartet. We'll now number the peaks, 1 and 2, and write down all the information we can get from each peak. So peak 1 has got a ppm of about 1.5. It has an integration of 3, so in these spectra the integration is given above the peak. And it is a triplet. We can see the peak here has been split into 3 peaks and it has the correct relative heights for a triplet, so there are 2 ways we could have identified that as a triplet. We'll do the same for peak number 2. It has a chemical shift of about 3.75. It has an integration of 2. And it is a quartet as it has been split up into 4 separate peaks. In this case, we can now easily match up the peak to the environment. It's quite easy to see that environment A should be peak number 1, and environment B should be peak number 2. Now, we've made this easy for ourselves by clearly setting out the information that environment A gives us, peak 1 gives us, environment B, and peak 2. For example, we know that environment A has got 3 hydrogens, peak 1 has got 3 hydrogens. Environment A should be a triplet, peak 1 should be a triplet. If we went into more detail, a chemical shift of about 1.5 would match with a CH3 proton approximately. Our peak for a CH3 is about 0.7 to 1.2, but given there's an electronegative group on this molecule, we can expect everything to be shifted slightly downfield. So that makes approximate sense. The ppm values are only a rough guideline. So if we've got something of about 1.5, it could still be an RCH3. We have to take into account how close it is to other electronegative groups, in this case the chlorine, which will have an effect on it. Environment B is clearly peak 2, as they both have 2 hydrogens. They're both a quartet. The exam question might ask you to explain how you came to your judgment assigning the peaks, and you could then write sentences explaining each of these facts we've set out here. By setting out your work really clearly like this, it makes it obvious to the examiner that you know what you're doing and how you've assigned the peaks, and it prevents you making any silly mistakes trying to do this process in your head. We'll now look at 2-chloropropane. So we'll draw out the structure of the molecule. We'll then assign and label the environments. And we'll then write down all the information we can gain from the environments. So starting off with environment A, there are 6 hydrogens in total in environment A. Environment A is adjacent to 1 hydrogen. Remembering, we only look at a single example of A, so we'll look at the left one for example. There is 1 hydrogen adjacent to it. Using the n+1 rule, 1 add 1 is 2, so environment A should be a doublet. We'll then repeat the process for environment B, so there is 1 hydrogen in environment B. It is adjacent to 6 hydrogens in total. Therefore, it'll be a multiplet, as 6 plus 1 equals 7, and anything with an n+1 value of 5 or greater we can call a multiplet. We would then label the peaks, in this case 1 and 2, and we'll then go through what information each of the peaks gives us. So starting with peak 1, it has a chemical shift of about 1.25. It has an integration of 6. And it is a doublet as it is split into 2. Peak 2 has a chemical shift of about 4.1. Its integration shows it has 1 hydrogen in that environment. And it is a multiplet as it consists of more than 5 peaks. As before, once we've written out all the information, it becomes quite easy to match the environment to the peak. In this case, peak 1 is environment A, as they both have 6 carbons, and it is a doublet as predicted. The chemical shift of 1.25 is approximately correct for an RCH3 group. Remember, we have to take additional electronegative groups into account. In this case, the chlorine will cause everything to be slightly downshifted. Peak 2 is environment B, as it has got 1 hydrogen as predicted, and is a multiplet as predicted. It is a chemical shift of about 4.1, which falls within the range for a hydrogen attached to a carbon attached to a chlorine. So being quite satisfied that we've assigned these peaks correctly. Remember, as we looked at with the carbon NMR examples, you might be given 2 molecules and asked to determine which spectra belongs to each molecule, so you'd have to go into the further information provided by each peak to establish which molecule belongs to which spectra. We'll now look at butanone. So we would draw out the structure of butanone. We would assign and label each of the environments. and then look at all the information each environment gives us. So for example, environment A consists of 3 carbons. It's adjacent to 0 carbons, so we'd expect it to be a singlet following the n+1 rule. Environment B consists of 2 hydrogens. It's adjacent to 3, so we'd expect environment B to be a quartet. Environment C consists of 3 hydrogens. It's adjacent to 2, therefore it should be a triplet. Even if you're writing this down, you think it's quite straightforward to assign the peaks, we should still write all the information the peaks gives us, as that could be worth additional marks in the exam. So we're still going to label each of the peaks 1, 2 and 3. Peak 1 has a chemical shift of about 1, it's got an integration of 3, and it's a triplet. Peak 2 has a chemical shift of about 2.1, it has an integration of 3, and it's a singlet. Peak 3 has a chemical shift of 2.5, it has an integration of 2, and it's a quartet. Therefore, peak 1 is environment C. As we can see, the information for these match up. It's a triplet with 3 hydrogens in its environment. Peak 2 is environment A, as it's got 3 hydrogens and it's a singlet. And environment B is peak 3, as it has got 2 hydrogens and it's a quartet. If you look at the chemical shifts, they also make sense, as the most electronegative one, in this case, which could be either B or A, and much further downshifted from C, which is going to be the least electronegative group. Finally, we're going to look at 2-chloro, 2-methyl butane. We would draw out the molecule first. We would then draw and assign the different environments, and then look at the information provided by each environment. So in this case, environment A has got 6 hydrogens in it, it's adjacent to no hydrogens, so it's a singlet. Environment B consists of 2 hydrogens, it's adjacent to 3, so it'll be a quartet. And environment C has got 3 hydrogens, adjacent to 2, so it's a triplet. We'd label each of the peaks. Peak 1 has a chemical shift of 0.8, consists of 3 hydrogens, and is a triplet. Peak 2 has got a chemical shift of 1.2, has got 6 hydrogens, and is a singlet. Peak 3 has got a chemical shift of 1.8, has got 2 hydrogens in the environment, and is a quartet. So, matching up the information, peak 1 will be environment C, peak 2 environment A, and peak 3 environment B. You might notice that, just like the previous example, this one consists of a triplet, a singlet, then a quartet. However, you could tell the 2 spectra apart by comparing the integrations and the chemical shift values. So you have to use more than just a splitting to assign a molecule, because you could have, as we've just seen, 2 examples which consist of the same number of peaks with the same splitting, but the chemical shift and the integration will be different for each example. So you have to make sure you use the full range of information available when assigning NMR spectra.